Thanks, Andrea. Just wanted to thank the conference organizers for the invitation to be here. It's been really stimulating so far. Today I'm going to be talking about basically shining light through a transparent crystal, which sounds incredibly boring, but hopefully I can convince you that it's not as boring as it sounds. But basically what we're going to try to do with this subgap light is to break electronic symmetries specifically, right, targeting the electronic degrees of freedom. And we're going to try to do this by inducing subgap photocurrents. So already I think the title should be a little controversial because subgap photocurrents are a topic that I think is still controversial in the theoretical literature at least. In particular, we're going to use materials that have broken time reversal, okay? And that's the way that we're going to try to get around this subgap scenario, okay? And if that didn't make sense to you, hopefully it will as I go on. Okay, so before I really get started with the meat, I just need to say that Jinshu Zhang, who's a postdoc in my group, led this work. He's moving on to a faculty position shortly. Assisted by graduate student Tyler Carbon, we've got theoretical support from Adrian and Daniel, primarily, a postdoc at UCLA and a postdoc at Rutgers. And Sang Chong's group provided the crystals for the experiment, but also the initial ideas that seeded some of this work. Okay? Okay. So, I think, Jun pointed out yesterday that a lot of the ideas behind this idea of Floquet was born out a long time ago, but I think, recently a lot of us have been inspired by the fact that you can actually visualize these things in condensed matter systems. On top of that visualization, we've also seen that you can actually use this Floquet protocol to engineer material properties in certain ways. So, famously, James and Andrea were part of a work that showed that you can get a anomalous Hall effect by sort of using circularly polarized light to hybridize bands and obtain a Berry curvature, right? David's group not too long ago showed that you can modulate the nonlinear optical properties of certain materials by shining light through the gap. And this is essentially, you start on resonance for the second harmonic, you shine light through the gap, there's a repulsion, and essentially you go off resonance and some of the SHG disappears, right? And previously, there was a work that showed that if you shine circularly polarized light on 2D materials that you can get an optical Stark effect. Again, an energy shift due to the interaction, using light to sort of create a band repulsion. Right? And so the question I'm going to ask in this talk is related to these, which is to shine light through a gap, and can you actually engineer the point symmetries of the crystal? Okay? Can you actually break rotational symmetry? Can you break other kinds of symmetries, that besides time reversal that have been really shown in these works? Okay? And the reason that I want to actually approach this is because this question is actually born out of trying to see light-induced photocurrents, okay? And so just for a moment, time reversal symmetry is really important here, so I just want to review something we all know, which is to just look at Ohm's law. And if we apply time reversal symmetry to Ohm's law, you can see that under the time reversal operation, J goes to minus J, and E goes to E, okay? Everything is fine. If the material possesses time reversal symmetry, your transformed sigma prime needs to be equal to sigma, and you come up with the brilliant equation that says J is equal to minus J, and that has to be equal to 0. So you can't have current in a system in which you have time reversal symmetry, right? That's the conclusion. So that seems a little weird, but obviously we know the loophole here. The thing that's wrong with this conclusion is that we haven't considered dissipation. So if the system does not have broken time reversal symmetry, it has to be dissipative to carry current, at least a linear order. Actually, it's true to all orders, but yeah. I've only shown it for linear order here, right? And so dissipation is actually extremely important to this process. And so, this is the scenario we just talked about.
What happens in a superconductor?
In which case?
I mean, it doesn't dissipate, it carries a current.
Are you talking about Meissner current, or are you talking about?
I run a current through it.
You run a current through it. That's in a metastable state. So if you think about a loop, right? You need to apply say, magnetic field. You pull it down, and it gets stuck in a excited state in which it's carrying current in a loop, and that actually breaks time reversal. Anyway, a current carrying state has to be a broken time reversal state, by the way, right? You go, say, from the n=1 state, you get stuck, say, in the n=1 state, and that state it has angular momentum and it carries current, right? So it's broken time reversal. Anyway, so if you have a time reversal symmetry unbroken, right, you need to dissipate heat. Now, if you break time reversal, right, so in the case of the quantum Hall effect, integer quantum Hall effect, or in the quantum anomalous Hall effect, you either have to apply an external field, or you have to have a magnetization to get a current, right? And in this case, this is dissipation-less, and in this case, dissipation. So if you want to have dissipation-less current, you got to break time reversal symmetry. Okay, there's relatively simple considerations so far. In this case, the question I'm going to be talking about today is going to be talking about photocurrent, okay? Arguments are going to be somewhat similar. If you apply time reversal symmetry to this equation, it doesn't really change, right? You got to break time reversal symmetry somehow to have photocurrent as well, right? And there's an extra condition, which is that parity also must be broken because J transforms to minus J under parity, but the E's, there's two factors of E, so you got to break parity as well, okay? So there's two ways to do this. So normally what we do is we have a semiconductor or some kind of ferroelectric or something, which we shine light, and all of a sudden you get some kind of current, say a shift current or something like this, right? So in this case, what you have to do is you have to have above gap excitations, right, to carry this current. Now, you can have time reversal symmetry broken by the material, but this has been very infrequently investigated. Okay, so no one has really taken a time reversal symmetry broken system and asked the question, can I get dissipative or non-dissipative current, photocurrent, by shining light through the gap of a time reversal symmetry broken system? And that's what we're going to try to attack today. Okay, now I shouldn't have said nobody has asked this question. Actually, a lot of people have asked this question, and I'll show a few papers in just a second. But one of the important things about the fact that parity must be broken and time reversal must be broken to get this non-zero photocurrent is the fact that I'm going to be choosing a system in which PT symmetry is preserved. Okay, so basically what happens is the magnetic system breaks inversion. Okay, and the reason that I want a system that has PT preserved is because that's very restrictive in terms of what you can see when you shine light through the gap. So if you shine light through the gap, in principle, in a regular system that has parity breaking through the crystal structure, you can get a rectified dipole moment. In principle, you can get a magnetization or injection current, some stuff, stuff related to, you can get other effects is what I'm trying to say. But if PT is present and you shine light through the gap, note that if I apply PT to this equation, if PT is a symmetry, this thing is going to vanish. If PT is a symmetry, this thing is going to vanish. If PT is a symmetry, this thing is going to vanish. This is the only term that survives. Okay? And that's because of, for instance, take the magnetization. Under PT, this is going to flip sign, right? Under PT, these two are not going to flip sign, and that's got to be 0. Under PT, the polarization is going to flip sign, but the right-hand side will not, and this is going to vanish as well. So PT is a very restrictive symmetry, which leaves only this term.
Provided that sigma 2 is different from 0.
Provided that sigma 2 is different from 0. What do you mean by sigma 2 is different from 0? Yes, in principle, yeah, sigma 2 is different from 0. Yes. Provided that sigma 2 is different from 0. Very good. Okay. So, are subgap photocurrents possible in a magnetic system? I don't know, but there's a bunch of people that have been trying to answer this question. Okay? There's a whole slew of papers that have come out in just the last few years trying to ask this question. Some of them take a Floquet approach. So this paper says not possible in a insulating system. but could be possible in a metallic system, where there is an optical gap, but it's metallic, okay? There's a few papers that says, this paper, for instance, agrees with them. This paper says you can actually get subgap photocurrent. This paper agrees with this one. So you have two papers that say you can and two papers that say you can't. By the way, I've only chosen these 4 papers to show there's more. There's much, much more. And I'm sorry if I left you off and you're in the audience, right? But these just fit nicely on this slide. That's the only reason I chose these papers. Jonathan.
But so I guess this is presumably restricting our attention to only response to electric field, because you can also have magnetic response mixed.
Yes, very good. Yeah, so they're talking specifically about J is equal to sigma EE, that response.
Is it really clear that you can tell the difference between a response due to E squared and a response due to like E times B?
Yeah, that's a great question.
Polarizations presumably have the same kind of selection rules.
That's a good question. Under time reversal, it's different, right? So if I had a J is equal to EH, that's restricted by, again, PT.
It's compliant, right?
It is, it's not allowed. Oh, it's not allowed under PT because B doesn't change sign under inversion.
But under T,
but
so
PT it doesn't work.
P
PT
is broken, T, or, okay, maybe.
Yeah.
PT,
the combined PT, it doesn't work. It's not allowed.
Okay.
Yeah. Yeah.
So, thank you. Yeah, Chairman. Yeah, there you go. Let's see. I can't work with this. So, just one question. For sigma, when you look at sigma 1, the integral of sigma 1 is the number of charges somehow.
Yes.
In this case, is sigma 2, for sigma 2 to be non-vanishing, do I need to have doped charges in the conduction band?
For sigma 2?
To have any
so this is the controversial point.
terahertz photocurrent somehow, rectified photocurrent.
Yeah, so this is the controversial point. So some of them, this is what I was trying to say, some of the theorists would say you can, and some of them will say
But is there a sum rule? In sigma 1, I know the answer, right? The integral of sigma 1 is if there's no charges, sigma 1 is 0.
Right.
Yeah.
Right. Is there a sum rule? I believe that there is, but I don't think it is as strong as that. Yeah. Okay. Very good. So, so the material we chose to look at for our experiment is chromium oxide. Okay, it's a classic system, been studied since the 1960s. PT is preserved in this system. And the nice thing is it becomes an antiferromagnet at relatively high temperature, above room temperature. And what we're going to do in this system is actually pump just below the gap. The gap has, the first optical transition, the first DD transitions at 1.7 eV, so we're going to pump at 1.2. So quite off resonance, okay? And you can see the crystal structure looks like this. Once it magnetically orders, you have, spins that either go in a down-up configuration. If you, in this domain and in this domain, it goes in an up-down configuration. So you have two choices of domains. You don't know which one's going to form a priori, right? Or which one you're going to look at a priori. Okay, so you can actually see PT is preserved very easily. This is the inversion point. So if I apply inversion symmetry, this spin gets mapped to this one, and it goes to the other domain. Once you apply time reversal, you come back to yourself. So PT is preserved. Okay? All right. So what we're going to do to try to see if there is a subgap photocurrent is we're actually going to use second harmonic. And the reason that we use second harmonic is it's because it's actually very sensitive to the electronic degrees of freedom. Okay? And we're going to try to see a symmetry breaking response here. The way that we do this experiment is essentially we come in at normal incidence to the crystal at a frequency omega. It comes out at a doubled frequency 2 omega. And we're going to have some pump light go through the crystal. As I said, it's just in the transparent region of the crystal. In principle, no light is absorbed if there's no multiphoton absorption. Okay? Or Raman processes, et cetera. Okay? All right. So, this comes back to kind of Jonathan's question, which is, we usually think about second harmonic in terms of electric dipole second harmonic generation, but there are higher order processes that can occur, right? There's magnetic dipole, SHG, there is quadrupole, SHG, et cetera. For our particular study today, it turns out that magnetic dipole SHG is actually quite important. And I'll show you why in just a second, okay? But essentially there's two terms that go into the radiative source term. And so we end up with for say an electric dipole source. We plot the intensity in a rotational anisotropy pattern. You know, a lot of you are very familiar with this, right? But the point is you can get two sources of radiation, magnetic dipoles oscillating and they will radiate, and electric dipoles oscillating and they will radiate as well. Okay? The reason that this is important is because they're relevant to the parity selection rules of the crystal. So let's just go through this really quick, okay? I know a lot of you know this, but let's just go through this really quick. So each transition for a second harmonic is associated with a particular matrix element, right? And the matrix element will look something like this. So if we consider the electric dipole operator, which is odd under inversion, if our crystal is centrosymmetric, all the eigenstates must be either even or odd, right? So let's imagine I started in an even state. You have a matrix element, you know, electric dipole matrix element take you there. So you start in an even state, you'll end up in an odd state. You start in an odd state here, you'll end up in an even state there, and then this emission is forbidden because you're going from an even state to an even state, which is forbidden with electric dipole SHG. Okay, so a centrosymmetric crystal cannot give you electric dipole second harmonic generation. However, if you look at the magnetic dipole operator, this is inversion symmetric. Therefore, what can happen is if you have a centrosymmetric crystal, you start in an even state, you go to the odd state with an electric dipole transition, odd back to even electric dipole, and you can emit magnetic dipole radiation in the second harmonic. That is possible, right? So magnetic dipole radiation allowed in a parity symmetric material, electric dipole radiation forbidden. Okay, usually magnetic dipoles, second harmonic generation is a lot weaker. So what we do in this study is we resonate with a particular transition that's magnetic dipole allowed. So we boost that signal. Okay? The important thing about this study is that because you have two radiative sources, you can actually get interference between the electric and magnetic dipole radiation. Okay? So you can almost think of it as an interferometer. There's two paths that I can go up and come down. Okay? So I have two photons take me, I can emit through magnetic dipole or electric dipole radiation. And so emission can take two paths and they can interfere. And these two paths are obviously not external, they're internal to the atom, but nonetheless, it's not a nice visualization of what's going on. Okay? So let's actually look at some of the SHG. So I'm not driving the system yet, I'm just looking at the system in equilibrium. I'll show the driven data in a bit. Okay? So what I'm doing here is to look at a resonant process, right? So this is the second harmonic process. I'm resonating with this level, and what I can get in the Néel disordered state, so in the disordered state without Néel order, right, no spins here, is that I can see magnetic dipole radiation. Parity hasn't been broken, so this is the term that is allowed here. Okay? You can see the pattern here is characteristic of the crystal symmetry, right? It's a threefold crystal. I'm shining light along this direction, right? And so it's got to respect the threefold symmetry of the crystal, and it does. Very nice, okay? It goes as a sine 3 theta. Note that I'm plotting the intensity here, so you got to take this term mod squared, which is why you end up with a pattern that looks six-fold symmetric. Okay. All right, so now when I cool it down, I go below the Néel temperature, and what happens is I pick up a second term in the second harmonic. Now electric dipole second harmonic is allowed, and these two terms now interfere. It turns out that I get a cosine 3 theta for the electric dipole, a sine 3 theta for the magnetic dipole, and when you add these two terms together, the nodes lift. Okay? The nodes lift actually for a very simple reason, which I'll explain to you shortly, but essentially what we're seeing is two terms that actually interfere. So let's think about the interference for just a second. Okay? It's a very simple reason, but let's just go through this math really quick. If I have these two terms, so let's imagine that the magnitude of the two terms was equal, right? And let's imagine that there's a phase difference of pi over 2 between them. I could write this term as chi m, then my sine 3 theta plus I cosine theta I can write as e to the I 3 theta. When I take mod squared of this term, I get a constant, and therefore there's no dependence as a function of angle. The node gets lifted, and I have a perfect circle. Okay, radiates in every direction. On the other hand, if these have the same phase, and they're equal in magnitude, I have a sine 3 theta plus cosine 3 theta, which I can write as sine 3 theta plus pi over 4, which just says that my SHG pattern will rotate with respect to the crystal axis. So node gets lifted for a particular phase, which is pi over 2, and it rotates for when I have a real component, okay? So by noting how much the node gets lifted and how much the pattern rotates, I can actually figure out the relative phase between the electric and magnetic dipole components in this interference experiment. Okay? Okay.
Can I ask a question?
Please.
I mean, of course, this homodyne measurement is great.
Yeah.
Unless you have some spurious second harmonic. So in all practical cases,
yes,
you'll have some second harmonic going around your table, which will beat with that and give you also a heterodyne component, which will then change all your flowers.
What do you mean will beat?
I mean, if you have second harmonic coming from a mirror or anything, or the surface of the crystal, which basically will happen always, you'll also have terms where this local oscillator, which will be the other second harmonic, will beat with each one of these.
Yeah, sure. I mean, so what you're saying is I don't need to do this fancy.
No, you do need, but there's other terms that will come in which may change the way these flowers look. So unless you have a local oscillator which you scan, and then you exactly understand what that's doing,
We exactly understand because we scan the wavelength.
That's not what I'm saying. Unless you have an additional controlled second harmonic of which you change the amplitude in a controlled way, and you look at how these flowers scale with this well-controlled local oscillator, you may get confused.
I mean,
I've learned the hard way.
Yeah, I mean, there is this. I think we can be pretty confident, and I'll show you evidence shortly of why we can be pretty confident that this is bulk SHG. Okay, I don't think there's any surface contribution here. But I'll show you evidence in just a second, okay? Anyway, my point is that, by changing by looking at the interference between these two terms, we can figure out the relative phase, okay? And I can actually plot the relative phase as a function of wavelength in this crystal, right? So if you look at certain wavelengths, you see the node is lifted, right? So I know that I have a relative phase of pi over 2. At other wavelengths, I have a relative phase of 0. So I can plot, so I've just taken here roughly minus 90, plus 90. You can see the node's lifted. The pattern hasn't really rotated from the crystal symmetry. And in these two cases, I have roughly 0 phase difference. Okay? So I can map out in this interference experiment what the relative phase is between these two components. Now, why is this relative phase changing as a function of wavelength? It's because I have all of these DD transitions in the way. Every time you cross a transition, there's a change of phase by pi in principle, right? So you cross a DD transition, phase can change. And that's essentially what this is coming from. So we can actually map out the resonance structure of the magnetic dipole component and electric dipole component. They don't exactly line up, and you can go to these various places and measure a phase difference.
So how do you ensure that the two susceptibilities are equal? I mean, because
very good.
You're changing the wavelength?
Very good, very good. So you can actually tune this by changing depending on how strong the antiferromagnetism is, right? You can actually go to a temperature where they're roughly the same magnitude. Note that the electric dipole component is actually quite weak because it's coming from spin-orbit coupling, right? So your electric dipole component is already quite weak. You boost your magnetic dipole component with resonance. And you can sort of play with temperature and wavelength and find a nice spot where they're roughly the same magnitude. Okay. So this is exactly what I was saying. So if you look at the temperature dependence, so when it becomes antiferromagnetic, you can see the node gets lifted as you cool it down, and you just go to some temperature where it's the order parameter is large enough, and you can find a nice spot. Okay, so this has been done before. In '97, Fiebig had shown this with circularly polarized light. Here we did it with linearly polarized light, mapping out the phase very carefully. Yeah. Okay, so one thing I want to emphasize is that when we choose a phase here that's actually pi over 2, right? We decided to work at this particular wavelength for a reason that will become clear shortly. But when we look at the domains with linearly polarized light with this phase difference of pi over 2, you can't actually tell the difference between the two domains, right? Because you have the magnetic dipole term, which stays fixed in the two domains. You have the electric dipole term, which flips sign between the two domains. But because there's a phase offset of pi, you have basically an a plus ib and a minus ib mod squared. You're getting a squared plus b squared both times. So there's no difference, okay, in the two domains. All right. However, if you use circularly polarized light, Fiebig had showed back in the early 90s, this was the first picture ever taken of antiferromagnetic domains with nonlinear optics, and he showed a very beautiful image in chromium oxide that you could actually see the domains using this method of interference. Okay, and it took him about 10 minutes to collect this image, which is actually quite impressive compared to using other techniques. Okay, so great. Okay, so this is just a quick summary of what I've done so far. I haven't even shown light through the gap yet, and I'm just going to do that right now. But basically, there's two contributions to SHGs, magnetic and electric dipole. One is there above and below T-nail. One is only there below T-nail. Okay, and because of this internal interference, now our probe is phase sensitive, which is nice, right? So now we're extremely sensitive to the subgap light, even though we're off resonance. And we can choose the phase by selecting the wavelength. Okay, I'm just going to pause here to see if you have any questions before I go and drive the system.
Yeah, you said you were pumping a magnetic dipole transition resonantly?
Yeah, I don't want to use the word pump, but I'm probing. Yes, but yes, yeah.
Well, I'm confused because you're looking at a bunch of different frequencies.
I'm looking at a bunch. Yeah.
How do you target? I'm confused. And could you explain again what you mean by resonantly driving the magnetic?
I do not want to use the word drive because I haven't shown my pump yet. Okay. But what I mean is just that with my probe, what I'm doing is I'm just looking at what's going on in the system by looking at a particular DD transition. I'm just looking at what's going on right now. Okay? And this is a magnetic dipole allowed transition.
Okay, I see.
Okay? So above T-nail, when I look at what's going on through this magnetic dipole channel, I can see what's going on. I can see the symmetry of the crystal using magnetic dipole radiation.
Okay.
Okay? Below the nail temperature, I have two components, magnetic and electric dipole radiation.
Can you repeat the argument why there is no surface component here? Why can you be sure that there's no surface component of SHG?
if you look at, you mean like how do I know that I'm looking at magnetic dipole?
Bulk. How do you know you're looking at bulk?
Because I'm literally resonant with that particular transition. If I go off resonance, I don't see anything anymore.
But in the heterodyne, you would still generate on the surface, but simply heterodyning differently the field.
I mean, so what you're saying is this could be magnetic dipole SHG from the surface.
Yes.
Is that what you're saying?
It could appear in the interference.
Or you're saying I could have electric dipole from the surface.
You could have everything from the surface. Yes, both.
Yeah. Well, I mean, okay. So the reason that I know it's magnetic dipole first is because I'm literally resonant with a magnetic dipole transition, right? And if I'm going to have a surface component, that will likely be electric dipole, right? Because that's the surface breaks inversion, right? So I'm likely to get, yeah.
Second harmonic that comes from the quarter wave plate, that comes from anything that you have in the path of the laser.
They don't have these transitions.
I understand, but it will be a beat term that comes on these resonant things, right?
I mean, yes, there might be some small contribution, but literally I'm boosting my signal.
So maybe the argument is that the electric dipole is much larger than any other spurious second harmonic that comes from everything else, right? So
the electric dipole and magnetic dipole.
The electric dipole, which acts as an interfering term.
I mean, that only shows up below T-nail.
Okay, then I don't even understand why. Okay, anyways, yeah, to be continued.
You have the flower pattern.
Yeah, that's also it's the crystal. It's the crystal. Yeah, there's a lot of evidence here that like what we're doing is the interpretation is correct. Yeah.
Sorry, but just quickly back to the other question. So I'm a little confused.
Okay.
So you say we're probing the specific transition resonantly, which is why we can focus on the bulk contributions, but now as you sweep the probe wavelength, we're coming off resonance, right?
Yeah, you can go off resonance, but we're basically looking at in this range where there's a bunch of transitions. So you can see, you're sort of going off resonance. If you go especially down, or if you go down here, you basically go completely off resonance once you go in sort of like this region. But
okay.
Yeah.
So you say we're sweeping the probe wavelength, but we're still close to the resonance.
Yeah. We're still close to like a bunch of little splittings due to the crystal. Yeah. This is essentially, all of these levels actually correspond to this 4T2G transition, but they're just split by crystal symmetry and, spin orbit coupling, et cetera. Yeah. Okay. All right, any more questions before I move on to actually drive the system? All right, let's go. Okay, so now what we're going to do is we're just going to shine light in the transparency window. Okay, presumably nothing's going to happen, but of course something does. Otherwise, I wouldn't show you this data. And we're going to show that hopefully we can use light to generate photocurrents. So this is what we see. Okay, so you shine light in the gap, in the transparency window, and you go from this pattern to this one over here. The light that we use is actually linearly polarized along this direction here, in which I've shown the arrow, right?
Same color as the first amount.
No, different color, right? This is 1.2 eV, right? Whereas that one was in the region of 1 eV. Okay, so the drive does this to the system, and you can ask, okay, so what's the time scale of this effect, right? That's the first thing that Andrea would ask me, right? Okay, here's the data. So our pulse width in our experiment is 180 femtoseconds, and we essentially see the pulse width. Okay, so you see that the symmetry is sixfold before the pulse goes through. It's sixfold after the pulse goes through, but as the pulse is going through, you have this broken symmetry. Okay, so is the broken symmetry a photocurrent? Maybe not, right? So we got to show, or at least argue. But as I've shown you earlier, because of the restrictions based on PT symmetry that is present in the material, it hints at the fact that this might be photocurrent. Okay? So you can ask, I think most of us would be convinced that this is a purely electronic effect, right? Because it's happening so fast. But just to show you, other people have taken data on this to show that the lattice effects and the magnetic effects happen on a much longer time scale. Okay, so the lattice effects and magnetic effects happen on a time scale of a few picoseconds, and we're talking about 180 femtoseconds. We don't even see any relaxation here, right? Okay, so so it seems to be associated purely with the electronic subsystem. We don't need to touch the structure or the magnetic structure, in fact, right? Okay, so you can ask, is this actually related to the magnetism, right? Because I made a big deal in the beginning about how you need to break time reversal symmetry to see this effect. So you see that at 305 Kelvin, when the system is still in the paramagnetic state, there's no broken symmetry when you shine light through the gap. Okay? But as you cool, you can see that the symmetry starts to break more and more as we shine the light through the gap. And if you plot the symmetry breaking, I'll explain to you what this term is in just a second. But if you plot what is essentially the symmetry breaking as a function of temperature, you essentially see that this picks up also like an order parameter. So the symmetry breaking effect seems to be related to the order parameter in some way. Okay? Yeah.
So how is the polarization related to the butterfly axis?
I will show you in a moment. Yeah. Go.
5 minutes?
5 minutes. Okay. Okay, so what we can do is we can actually look at what happens if it indeed is related to the order parameter, right? It should be different in the two domains, and indeed that's what we see. So you go to one domain of the crystal. Note that again, these two look the same in with linearly polarized SHG before we shine light through the gap. When you shine light through the gap, you get two opposite signals in the two antiferromagnetic domains. So even though we can't see the difference between the antiferromagnetic domains, when you shine light through the gap in the transparency window, all of a sudden the identity reveals itself. Okay? It's essentially telling us that what we've done is to induce some kind of vector that's pointing in opposite directions in the two domains. Okay? If you shine circularly polarized light, absolutely nothing happens. So you shine light through the gap, circularly polarized light, right, left, absolutely nothing happens. You have to shine linearly polarized light to see this effect. Okay, so this is the question that Atach just asked. So if you have, if you change the polarization of the pump light, you essentially change this butterfly pattern, right? But note that the shape is actually not the same. You haven't just rotated this figure. If you look at this figure and this figure, for instance, those are not the same, right? But you do repeat every 60 degrees. So if you look at -50 and then 10, that's the same shape, but rotated. Okay? So there is some respect of the crystal symmetry that's happening here, right? But it's kind of weird, right? Okay. So this is the polarization dependence of the pump. And what we did, okay, so we had no idea what was going on at this point. So we just guessed a solution, Okay? We just said, let's imagine we have a perturbation to the magnetic dipole term, a perturbation to the electric dipole term that look like these. Let's just put those perturbation terms in and see what comes out. It turns out that this fits the pattern actually quite well, right? And so what we said is, let's just try, now that we have these perturbative terms, let's imagine that the light is inducing these perturbative terms so that when I shine the light, as I rotate the polarization, I'm just going to rotate these two terms. Okay, the first order thing that we did. So these black lines here are not fits. This one is fit. This one comes from the rotation of the perturbations. But there was a weird thing that happened when we did this. It turns out that when you rotate the polarization of light by an angle phi, so we rotate the polarization of light by angle phi, our fitting terms, so we had to rotate these two bubbles by an angle minus 2 phi. Okay? So that was a clue as to what was going on. And when we ultimately did figure out what was going on, it turned out that if you think about a rectified response, the rectified response, if you figure this out, if you work this out, there's a minus 2 in that term, and that minus 2 corresponds to that angle. Okay? So the rectified response is the right interpretation here. Okay? And, the rectified response tells you that, at least for low fluences, you should scale as E squared, and indeed, that's what you see. So, okay, it's some kind of rectified response. If you go out into the, high fluence region, this assumption breaks down, but then you really start to drive the system pretty hard. Okay, but in the low fluence region below about 20 millijoules per centimeter squared, this all works out. Okay. So, if you put all this together, you put in the SHG pattern as a function, with the induced rectified response, right? And you work out what the SHG pattern should look like. Actually, we've only fit this one, and now everything works out. Okay, including the fact that you switch when you go to the other domain, you have this rectified response. So we can work all of it. All of these patterns are all not fits. Okay, only that one is fit. All right. So why hadn't such an effect been observed before? Essentially because you don't have this. People hadn't really looked with this interference response, right? Because of the phase sensitivity, you can see that when you pump, when there's a pi over 2 phase difference between the magnetic and electric dipole signals, when you pump, you can see that this response shows up very drastically. You're off, when it's a 0 phase difference, you basically don't even see this thing at all. Okay? So the phase difference was key because now you're phase sensitive, okay, to observing this effect. Now, let's just return, is this actually a photocurrent? This is the question I can't definitively answer, okay? But just based on PT symmetry, this is the only term here that's allowed. Okay? These terms all vanish through PT symmetry, but there's a loophole here, right? The loophole is that what if there's dissipation? We come back to this same problem. Okay? If there's a little bit of dissipation, that can give you, for instance, a induced dipole moment. Because I don't need to respect time reversal anymore in this equation, right? And that can give you potentially an induced dipole moment. So you could imagine that in that scenario, what could be occurring is I generate a photocurrent. That current actually has to go somewhere, right? So if it builds up on the edges of my pulse, what's going to happen over time is that I'm going to have a polarization build up, right? And I will see maybe a dipole moment. That was our interpretation in our original paper. I don't know if it's correct. It may be that there's current and that's all there is. That's what we're seeing in this, okay? I don't actually know. So you can ask, where would a dissipation channel come from? You can actually see when we look at our data, this is before time 0, this is after time 0. That line is not at the exact same spot. There is some kind of absorption process here. It's probably 2-photon absorption or Raman process or something, right? There is a little bit of absorption. I don't know if that's key to the process, but anyway, it's there. So I might as well point it out. So anyway, I'm done. The questions to consider is dissipation key? Is this actually a current? If it's a current, where does current go? Does it ultimately give rise to a DC polarization? I don't know the answer to all these questions. An interesting future experiment for us is to think about a Corbino geometry. If there was a current, maybe it will just flow in a circle, okay? But I don't envision that being possible anytime soon. Anyway, that's all I have to say. Thanks.
Okay, I'm going to exploit my position of power to ask the first question. There's one aspect, devil's advocate. Mm-hmm. Your pump will exert a Raman force on the crystal fields, on the octaedra, on the oxygen octaedra mm-hmm. of your chromium oxide, which will move all your levels
You mean like as in like a shift?
Yeah, I mean, let's say you have your octahedron, there's a Raman force which is either going to dilate it or compress it. Let's say it dilates it, and now the crystal field levels are going to shift.
So are you talking about some kind of electronic process? Because again, the time
No, by
scales are very fast.
a Raman force. Basically, what happens is that by impulsive stimulated Raman, which with femtosecond pulses is going to displace the atoms.
So you would see that in the response. My point is that like
No, but all the interference terms, because you rely on being close or far away from a resonance, may change. I'm just giving you. I'm not saying this is true. I'm just saying.
I think it would, right?
Yeah.
So one thing I will say is, at least within the resolution of our laser, we can't see any. We don't resolve any shifts. Okay, just to the energy levels at time 0.
Oh, you're sampling the frequency resolved response
We can
also on the peak of.
We can do that. Yeah, and we don't see an actual shift. Okay.
All right. Good.
Yeah.
So it sounds like from what you're saying, someone could equally well target an electric quadrupole transition?
Yeah.
And all the same, is this something you've considered? Is there a reason to
Yeah,
choose
yeah,
magnetic
yeah,
dipole?
it's definitely something we considered, and we didn't really care if this was magnetic dipole or electric quadrupole. You would have gotten the same thing. You could have gone to an electric quadrupole transition, and yeah.
Okay.
Yeah.
Yes, John.
But so this is a longitudinal photocurrent, you're saying? It's like EX,
okay.
X, JX.
So basically, the red arrows here are the direction of the photocurrent and the direction of the orange arrow. The orange arrows is the direction of the light polarization. And the red arrow is the direction of the photocurrent. So it's got this -2 phi relationship.
But at some points you have them non-orthogonal.
Yes, at some points they're non-orthogonal. In fact, at some points that I didn't take data at, they're actually parallel.
But then you should definitely have like heating or something, right? If you have J moving along E, then there should be absorption.
I shine light through the gap. There's no absorption of the light.
I mean, but charges are moving, and electric field is parallel to charge motion.
I agree with you. As I said,
maybe it's small, but
yeah. I mean, I agree with you, but again, time reversal symmetry is broken in the system, so I don't know.
But that's usually to like transverse Hall response, right? So E is this way, J is that way, so J dot E is always 0. You never actually dissipate.
Right. No, absolutely correct. I understand what you're saying. That being said, it's the exact same effect in the parallel direction as it is in the perpendicular, right? It's not a different effect. As I said, I can fit everything by just fitting one of them and rotating my perturbation and getting everything else.
Yeah.
Right? So whatever heating effect that is occurring here also has to be occurring in the other channel as well. And it seems like at least to first order, there is none. Right? I'm shining light again through the gap. Yeah.
So can you pass on?
So this is naive probably, but what is the band gap? I mean, why do you say that, I mean, you can absorb from this intermediate
there can be like 2
state.
photon absorption or something like this. Yeah. So those are effects that are possible. Either Raman effects that are possible. All of these things are possible. Yeah. So that's why I asked in the last slide, right? Is some kind of dissipation is present? I don't know if it's key to the process, right? Because I am. If you look at this, the symmetry is only really broken at the point in which the light is propagating through. There is 2 photon absorption at that point. There is, Raman processes at that point. There is going to be some kind of dissipation, right? I think it's unavoidable in this kind of experiment to have no dissipation at all, but it's unclear to me whether or not it's important. If it is present and it's important, you could have a rectified dipole moment. That's possible then, by symmetry at least. Right? But in all of those theoretical papers that were considered, they all assumed that you do have some, at least small dissipation. And so they all assumed that it was key. I'm trying to just play, just ask some questions to say whether or not it's really important.
Yeah. Devil's advocate part 2.
Yes.
I heard the word Floquet once. You mentioned Floquet drive. But where do I need Floquet to understand this effect?
Well, you don't need it to understand the effect. You can understand it in various different ways, right? But I think one way to think about what's going on is that you are essentially, because PT is preserved, but individually inversion and time reversal are broken. So you're your excited state band has a funny structure, which when you hybridize with the ground state band can actually lead to a current. Okay, so that's where it comes in, and that's where it's important.
But is it non-perturbative, or is it just a nonlinear like photocurrent? I mean, can I understand the perturbativity?
It's nonlinear photocurrent in this regime, like just basic. But once you go out into the high driving, it starts to become that you might be able to get away with doing more perturbation theory. I don't know, but in this regime, it's no longer just a second order nonlinear optical effect.
Okay.
Half a question, James.
Okay, so then continuing along these lines, is it possible to extend the pulse duration and see how long you can sustain, if it's Floquet or coherent artifact, basically how long it should follow your pulse before heating kills it?
Sorry, could you re-ask your question?
If you extend the pulse duration, you would expect, if it's a coherent effect, the signal should also extend with the pulse duration. So at some point it must kind of top off. So
I agree. At some point, some things. I don't know what that time scale is.
Okay. Yeah.
But yeah, I will say that in some region, this is just to throw another little interesting factoid out there. If you drive this hard enough, the reason that we weren't able to go further is that at some point the crystal just remembers that pattern for like 3 days. And I don't really know why that happens just yet.
That's interesting.
So I assume with a longer duration, you might get sort of weird metastable effects start to arise also.